All right, hey guys, and welcome back to another AP Physics C video. So this is a post-exam video. This is the first of many, hopefully. Today we're going to go over the electricity and magnetism exam because, well, I took both of the exams. They both went well, thankfully, and we get fives on both, God willing. But I think E and M was better than mechanics for me. So yeah, let's just jump right into this. This is the version I had actually, so we're just gonna go through the answers. So let's read this. An isolated air-filled charge capacitor consists of two conducting coaxial cylindrical shells that each have length L. The inner shell has radius R1 and the outer shell has radius R2, as shown in figure 1, where R1 is less than R2, which is much less than L. The surface charge densities of the inner and outer shells are positive sigma 1 and negative sigma 2, respectively. The absolute values of the total charges on the shells are equal. So this is going to be important later. All right, so this is the side view and the cross-sectional view. So part A says, using Gauss's law, derive an expression for the magnitude of E, the electric field, as a function of the radial distance r from the center of the capacitor for the region R1 is less than R, which is less than R2. Express your answer in terms of these constants. Okay, so this is what we want to visualize. So this is in between R1 and R2, correct? So we're just going to label that distance R. And that just helps us like visualize this a little bit. So they immediately, when they say using Gauss's law, what you should think is, okay, well, I'm going to write Gauss's law, right? Equals Q enclosed over epsilon naught. Great. So now we have to think, what am I missing from here? Well, we can start with either side, but what I'm going to think is Q enclosed. They didn't say we could use Q enclosed in these values, so we're going to have to derive Q enclosed. So let's think. Well, surface charge density is charge, well, I'm going to call it enclosed charge per area, right? Because let's think about it. For the Gaussian cylinder that we're going to visualize at this radial distance r, whenever we're using Gauss's law, we have to visualize like a Gaussian surface. We're going to visualize that Gaussian cylinder at that radial distance r, and we have to think, what is the only charge that it's enclosing? Well, the only charge that it's enclosing would be the charge density sigma 1. So if I derive the charge that sigma 1 holds, then that's the enclosed charge. So let's do that. So now, if I multiply sigma 1 by the A, which is the surface area of not the Gaussian cylinder, but the actual cylinder that's holding the charge, right? Because the Gaussian cylinder isn't holding the charge. It's the actual cylinder with the charge density. So sigma 1 times in the surface area of a cylinder is 2 pi, and the radius of the smaller cylinder, which has sigma 1, is R1 times L, and that's our Q enclosed. Right, so hopefully that makes sense. And now I'm going to take this whole expression and plug it into Gauss's law as my second step. Oh, my handwriting is terrible. So E dot dA is equal to, and it was sigma 1, 2 pi R1 L divided by epsilon naught. Now I can start looking at the left side of Gauss's law. So let's think, when we're using Gauss's law, what can we pull out of it? Well, we can pull the E out of the line integral, because the line integral, the electric field would be constant for all r's, right? It's not changing. It is changing as a function of r, but at that moment when we look at, oh my gosh, when we look at a single r, it's not changing. So that's why I can pull that out. And now this integral, this line integral, dA, is the surface area of the Gaussian cylinder. So let's go ahead and write that. So the surface area of the Gaussian cylinder is 2 pi little r L, because the Gaussian cylinder is not R1, R2. No, it's at R. That's where we're visualizing. That's where we want the electric field. That's why we put the Gaussian cylinder there. So now you can probably see there's a couple things that cancel. So we're going to cancel 2 pi, cancel L, and we'll divide by this R in order to get E by itself. And then we get this expression. The magnitude of the electric field is sigma 1 R1 divided by R epsilon naught. There's your final answer. Now we can move on to part B, or part AII. Derive an expression for the absolute value of the potential difference between the outer and inner shells, in terms of R1, R2, and sigma 1, and physical constants as appropriate. Begin your derivation by writing a fundamental physics principle or an equation from the reference information. So here, this is what we're going to do. We're going to think, okay, they just asked me to derive the electric field. If I have electric field, how do I get the potential difference? Recall that from your equation sheet, this is one of the equations. The potential difference is the negative integral of E dot dr, right? From points A to B. So when we're integrating for potential difference between 2 points, like it's saying the outer and the inner shell, what we're usually going to do is we're going to go from high potential to low potential, right? Or well, yeah, high potential to low potential. So high potential is at R1 because that's positively charged, and low potential is at R2. But because they asked for the absolute value for the magnitude, we're gonna put absolute value signs around both of these, and guess what? This negative just disappears, right? Because we have the absolute value, we don't have to care about that. So now I get that the absolute value is equal to the integral from R1 to R2. And now this E expression for that distance, remember we derived it from R1 to R2, so we can integrate that E in order to get the potential difference. And we'll sub in our equation right here, sigma 1 R1 R epsilon naught dr. Now this is looking like an actual solvable integral, so I'll pull out my constants. Sigma 1 R1 epsilon naught. See, we're doing it. And then we get R1 here on the bottom, R2, 1 over R dr. So now I'm just going to evaluate this integral. I forgot for a second. Sigma 1 R1 over epsilon naught. And now 1 over R will turn into, sorry, this should be like more curved, ln R from the bounds R1 to R2. Okay. And now we'll get sigma. This is a lot of steps, but what you could recognize at this point is that this will turn into ln R2 minus ln, I should zoom out so you guys can see the whole thing, ln R1. And then you use your rules of logs, and then you get this expression where it's sigma 1 R1 epsilon naught. This is your rule of logs. Whenever you subtract them, you can put them like this as if they're being divided, and this is your final potential difference expression. And the way you know that this is right is, let's think. The graph of ln x looks kind of like this. And I'll tell you right here, ln1 is 0. So at that point, this switches from negative to positive. So R2 is bigger than R1, like they told us. So if I have the natural log of a bigger number over a smaller number, that'll give me a number that's bigger than 1. So that will produce positive, right? And since we were asked for the absolute value, then we're correct because the absolute value is always positive. Now, if we went the other route and we integrated from R2 to R1, we would have ln R2 over R, or R1 over R2. But as we said earlier, R1 is less than R2. So that would give us a ratio or a value that's less than 1. And guess what? That would be negative. That's not absolute value. So that's incorrect. And that's a really tricky thing with electricity and magnetism. That's the hardest thing for me, at least, knowing how to define my integration bounds when I'm integrating for potential difference. Usually you can tell that if you're asked for like the absolute value or the capacitance, they cannot be negative. So go ahead and test that. So now we've derived that. And now question 3 is going to tell us, on the axes shown in figure 2, sketch a graph of the electric field E as a function of R from R equals 0 to a position that is outside the outer shell. Now this is where this thing that I highlighted comes back. The absolute values of the total charges on the shells are equal. So let's think about the last section first. So after R2, by Gauss's law, we know that the electric field is proportional to the enclosed charge, right? So let's think. When we draw our Gaussian cylinder out here, right, where R is greater than R2, right, in this area, what charge are we enclosing? It said the absolute values of the total charges on the shells are equal. So since this one was like negative, since this one was like okay, this is starting to mess with me now. No matter. Here, let me just, can I write now? Okay, well, since this one was negative Q, and this one was positive Q, and they have to be the same charge, then that means the charge that's enclosed, negative plus a positive that have the same number, is 0, right? If I'm adding, if I'm adding negative Q to positive Q, then there's no enclosed charge. Therefore, what we have to draw here, okay, sorry guys, technical difficulties. Can I draw on this now, please? Okay. Oh, no. Okay, great. Okay, so that means this has to be 0. So I'll write 0 there. And this also has to be 0, right? So because I'm enclosing no charge when my R is here and when my R is out there, then the electric field has to be 0. But in between, we derived that expression where electric field was proportional to sigma 1 R1 over R epsilon naught. So let's think about when R equals R1. It's not going to come up from infinity down like that, no. So don't do that because that's what I did on my exam and I messed it up. It actually has like a y-intercept kind of like this because this, when I sub in R1 there, I get a finite value. I don't get something that approaches infinity or that is infinity. So it'll kind of curve down like this because that's the trend that 1 over r has. That's what 1 over r looks like. And that's your graph. That's the graph that you want there. Okay, part B. This part was interesting. I almost messed this part up. So let's get straight into it. A material of dielectric constant kappa is inserted into the isolated charge capacitor such that the material fills with the region from R1 is less than R. So basically space between it, fills the space between it as shown in figure 3. Derive an expression for the capacitance C of the capacitor with the material inserted in terms of L, R1, R2, and physical constants as appropriate. Begin your derivation by writing a fundamental physics principle or an equation from the reference information. So this is what we need to recognize. Whenever we have a cylindrical capacitor, we can't, like you could use the capacitance equation, like C equals K epsilon naught, but then the plate area is a little bit different because one of the plate areas is different from the other one. So now, because the radius is different, right? So now we have to think, what's another way we can get to capacitance? Well, here's your answer. Q equals C delta V. And I can rearrange that equation to get C equals Q times the absolute value of delta V, because no matter what, like the capacitance has to be positive. So absolute value of delta V can be put there instead of delta V. So now, if I have the charge that's on the plates, which I derived earlier, so I technically could get this, and I have the potential difference from the earlier derived equation, which they asked me, right? Up here, they asked us derive the absolute value of the potential difference. Then logically, I could get to capacitance. So let's do that. Let's think about the charge again. So as shown earlier, sigma 1 times the plate area of 1, I'll call that A1, is equal to the Q enclosed, or big Q, because the charge is the same on both plates. And here they're asking for R1 and R2, so we'll see. Right, so that has to be the charge on both plates. So now I'm just going to write sigma 1 times 2 pi R1, because R1 corresponds to sigma 1, L is equal to Q. Great. So now I'm just going to take what I know here and solve for capacitance. So I know that Q was this. So I just showed that Q was this. And now let's divide by what's the potential difference? Well, the potential difference over here was sigma 1 R1 epsilon naught divided by that. Okay, so let's just plug all that in. Divided by epsilon naught times this ln expression. Bang. So now what can I cancel? I see R1 on the top and bottom, so I'll cancel that. And now I'm going to multiply by epsilon naught on both sides to get epsilon naught out of the bottom. And that will give me this expression. I'm going to get 2 pi epsilon naught L, right? Right? I'm asking. Okay, yeah. Okay. ln R2 over R1. Now, I should actually have called this C1 from the beginning. This is the original capacitance. Or, well, let's go back. Let's call it C naught. That's how College Board likes to talk about it. So C naught. This is equal to C naught. But now, after I insert the dielectric, we're going to use this fact that C naught times kappa is equal to the new capacitance. So this is an equation that's not on the reference sheet, but College Board requires you to know it. So now I'm just going to take that entire expression, 2 pi epsilon naught, and multiply kappa in order to get my new capacitance. Bang. That is your, oops, these are really bad lines. That is, oh my gosh. That is the final answer for that question. So hopefully that made sense. But yeah, let's move on to the next one. Wow, I ran out of space. Okay, guys, so bear with me. This is what we're gonna do. We're gonna select all. We're gonna delete it and move on to question two. Here we go. Nope. And this thing is messing with me again. Wow. Okay. See, I love my iPad, but like sometimes, okay, now it wants to work with me. Okay. Sometimes it likes to bug out. So let's do question two now. A rotating circular conducting loop of area A and resistance R is in an external uniform magnetic field of magnitude B that is directed in the negative z direction. At time t equals 0, the magnetic field is perpendicular to the plane of the loop, as shown in figure 1. The loop is rotating at a constant angular speed w with period t about the dashed line that is shown along the diameter of the loop. The value of the magnetic flux through the loop at time oh at time t is magnetic flux equals BA cos WT. Okay, so the last video I posted was the 2021 AP Physics C E&M questions. And after I made that video, I took the exam and I saw this question. It is the exact same question they asked in 2021. It is the funniest thing. Literally the same almost wording. They just here they're asking for what's this question? They're asking for max induced current instead of max induced EMF. And I was like, there's no way, right? They just keep pulling from past years. So this is why I like emphasize if you guys look at these videos, you look at the past year response, something could show up. So now let's look at this question. The absolute value of the induced EMF in the loop is absolute value of epsilon. The partially completed bar chart in figure 1 or in figure 2 represents epsilon at times t equal 3/4. In figure 2, draw bars to represent epsilon at time t equals 0, 1/4, and 1/2 relative to epsilon shown at, okay, so they just want us to fill in this bar chart. So let's think. This is a little bit more of a thinking question, so it might take me longer, so forgive me. Let's think at 3/4 t, what is epsilon? So if I logic this out, we know that phi, or whatever that thing, magnetic flux as a function of time, at time equals 3/4 t is BA cos W 3/4 times t. But what is t? Well, if it has angular speed v, then t is 2 pi divided by w. So now let's rearrange this. Let's think. It's BA cos W 3/4 times 2 pi divided by w. So these w's cancel, right? And now this becomes BA cos. Oops, I did something wrong. Forgive me. Okay. So that's the magnetic flux as a function of time. But here they're asking induced EMF, right? Hold on. This is not working with me. Once again. Okay, great. So this is the magnetic flux as a function of time. So what we need to consider is, well, they're not asking us for magnetic flux. Oops. They are not asking us for magnetic flux. They're asking for the absolute value of the induced EMF. And if you recall, this is Faraday's law. The absolute value is the absolute value of the negative derivative of flux with respect to time. So let's take the derivative of flux with respect to time. So that's BA, because constants go along for the ride. And the negative doesn't matter, because the derivative of cosine is technically negative whatever it is, but no, it doesn't matter. That doesn't matter. So because we have the absolute value symbol. So it's going to be sine WT, and then times W times W, oh my gosh, times, okay, times W because of the chain rule. So now this is our equation. So let's think. At time equals 3/4 t, what we said earlier, 2 pi over W is equal to t. So then 3/4 t is equal to 2 pi divided by W times 3/4. We'll simplify this a little bit. We get 3 pi over 2W. So now if I plug that into my sine equation, I get BAW sine 3 pi over 2 W over W. These cancel. Sine of 3 pi over 2 is -1. But the important thing is that when sine is 1, sine is max, right? That's just the property of the sine function. So then I know that the magnetic flux at that time is BAW. which is the max. That is the max, not magnetic flux, the max induced voltage. So here we know that that's going to be the max. So what other time will produce a max? Well, if you know sine is periodic function, so logically it will be here, right? This is when it'll be max. But let's also plug in just to see. So BAW sine and 1/4 t will be, and what was it? It was W times, okay, 1/4 t, we know t is 2 pi over W, so it'll be 2 pi divided by 4W. And this becomes sine of pi over 2. Sine of pi over 2 is 1. So that checks out. We get BAW both times. But now let's think about the other times. If I plug in 0 to this sine equation, sine of W times 0 is sine of 0, and sine of 0 is just 0. Knowing that sine is a periodic function, it'll be 0. The induced current will be 0 there, and it will be 0 here because sine is a periodic function, right? And I went through that a little quickly. If you guys want me to explain it further, I'd love to. Just ask me. So, yeah, that's how you do that bar chart. And now I'm second guessing myself because I think on the AP exam I just drew the bars. I don't know if I drew 0. I think I did. I probably did. I probably did. Okay, let's do part B. So derive an expression for the maximum induced current in the loop in terms of A, R, B, W, and physical constants as appropriate. Begin your derivation by writing a fundamental physics principle or an equation from the reference information. So this is what they're baiting us to do. They want us to write Faraday's law. That is what you should start with. Because in order to get to current, you need voltage. So let's write Faraday's law just out like fully. Now we'll sub in that magnetic flux equation. So basically what we just did, we're just kind of doing it again, but now we're solving for a value. It was BA cos WT. And now, like I said earlier, this will turn into BAW sine WT. And we know, this is what you want to write on the equation. We know sine is max at t, or no, sine is max at sine of WT equals 1. Therefore, if I set this equal to 1, E max is equal to BAW. Therefore, by Ohm's law, or you don't have to write by Ohm's law, you can just by V equals IR, I max is equal to BAW div R. Bang, done. I'm gonna minimize this now because we have to do other problems. Oh my gosh, I left it behind. Hold on, go back. But if that makes sense, maybe I can, hopefully that makes sense. But if you think about it from the calculus perspective also, when you're doing like the Lagrange error bound, you know that some functions will max out at specific values. And this is what I thought when I was doing this problem. I was like, okay, well, I know sine will max out at this value. So I know that the induced current will max out at that value as well. So now let's do part C. On the axis shown in figure 3, sketch a graph of the instantaneous power dissipated by the loop as a function of t during the time interval 0 to t, whatever it is. Well, we know, oh my gosh, we know, okay, you know what? I'm doing it over here. We know that P equals I squared R. But we know that E divided by R is I. So therefore, P as a function of time is equal to this as a function of time squared times, or no, divided by R. Right? But we know the, it says magnitude of power, right? No, it doesn't matter. Power is usually positive because this induced current, or not induced current, this induced voltage being squared will always make it positive because the square makes everything positive, unless it's I. You know what? Don't even worry about that. What I'm going to say, so we know this E of t, this epsilon of t equation. So we're just going to sub that in there. It's sine squared WT, and it's B squared A squared W squared because it was over here. It was, yeah, so this is going to get squared, but most importantly, that's going to get squared. So now we need to think. This is our power equation now. We need to think, what does sine squared look like? So normally, you guys, I have Desmos on here, but I ran out of space today. So what I would like for you guys to do is just go look at Desmos and think, where does this function max? So sine maxes out at pi over 2, which, if you noticed earlier, uh-oh, uh-oh, I think I did something wrong. Wait, no, I didn't. Haha. Okay. I was thinking I did something wrong on the AP exam. So sine maxes out when its value is 1. And that's when sine is pi over 2. So let's think. When pi over 2 is equal to w of t, well, what is t equal to, right? So like I said here, just based on the functional dependence between epsilon and power, when this is maximum, this has to also be maximum. So we know that this function will max twice on this interval. It'll max once at 1/4 t, and then again at 3/4 t. So you don't even have to logic it again. You could just draw it like this. Excuse, that is horrible, but excuse my writing. But that is what they want to see, right? But they just want to max here. They want to max at 1/4 t because look, if I plug in 1/4, right, of 2 pi divided by w times w, well, what does that give me? That gives me 2 pi divided by 4. Oh, wait, what does that give me? Pi over 2. Bam. This function will max at pi over 2. And it'll be 0 at 1/2 pi. Like, just citing that functional dependence again. So that will be your graph. And I guess I went through it a little quickly, but I say this like all the time. I'm sorry, you guys, but what we need to understand is that because these two are proportional to one another by this relationship, right? When this one maxes, that one will also max because there's no like phase shift. So when one is 0, the other one is 0. So here, oh my gosh. Okay. So here, now they're going to ask us, indicate whether the sketch you drew, I'm going to do part, oh my gosh. Oh my gosh. See, again, I love my iPad. I don't think my iPad loves me. It's okay though. Okay. So indicate whether the sketch you drew, in part C is consistent or not consistent with the bars you drew in part A. Briefly justify your answer by referencing the functional dependence between that and that. Okay, so that's what I was just saying, and that's the reason I was just saying it, because I knew they were going to ask this, because I've seen this already. So I know that P is equal to I squared over R. This should be your first thing. Or wait, no, not your first thing. You should say my sketch is consistent, and I'm just going to say is consistent with blah, blah, blah. My sketch is consistent with the graph I drew in part C because P is equal to I squared over R, which is equal to this squared over R squared times R, which is equal to this squared over R. Therefore, P is proportional to R squared. And so now we need to think when this is max, slash just this, because if it's squared, when a squared is max, the regular function will also max, right? It doesn't matter. Slash this is max. P is max. This happens at 1/4 t and 3/4 t on both. Excuse my handwriting. Graphs. Therefore, they're consistent. Now, if you have extra time, you can go back and make this a little bit more neat and like actually write stuff out. But that's what I did on the AP exam. I just yapped because I had some extra time. So that's kind of what you want to do. Excuse me for deleting it. If you guys need it here, I'll just pause for a second. Okay, so now I'm gonna delete everything so we can have more space for the next question. Oh, but this question. Okay, this is actually a pretty decent question. So let's get right into it here. So this is question 3. Describe, okay, in experiment 1, students are asked to graph to use a graph to determine the resistivity rho 1 of a circuit element that is connected to a variable power supply shown in figure 1. The circuit element is cylindrical and has uniform resistivity. The students have access to a voltmeter, an ammeter, and a ruler. Okay, so this is like they're baiting you to use these things. They don't want you to make up your own things like they don't want you to say a resistivity measure because obviously like what are you doing there? So they're going to say part A. Describe a procedure for collecting data that would allow the students to use a graph to determine rho 1. Include any steps necessary to reduce experimental uncertainty. So we're just going to outline like this. Step 1. Connect the circuit element ammeter and variable power supply oh my gosh, please, power supply in series after measuring the length L and um, radius R. We'll say, oops. Oh no. Not radius. It's not radius. Sorry guys, it's not radius. And diameter of the circuit element. So step 2 calculates the cross-sectional area. This is pretty boring. Cross-sectional, because like this step is always just so boring. Area A element using A equals pi d divided by 2 squared. Done. 3. And you know what? I could write this, and I probably will. So 3. So after you've done all that, what you want to do is you want to, this is another, oh my gosh. Connect the, this is important, voltmeter in series with the battery. It could be in series with the battery or the circuit element. It doesn't matter because Kirchhoff's loop rule dictates that they'll have the same voltage. So now, vary this voltage 5 to 10 times. So this is for less error. 5 to 10 times to reduce error. And now you could say like other stuff to reduce error. And measure V and I each time. Record both and increase voltage as you go. You go. Done. So yeah, my handwriting's bad, but the general idea is that if you increase the voltage, you can use V equals IR to find the resistance. And if I find the resistance, I can plot resistance as a function of L divided by A, and then, no, not resistance. Resistance as a function of, because R, if I have V equals IR, and I use like, oh, I'll show you guys in a second. But the general idea is that we'll use Ohm's law and the resistivity law to solve for this part B. So part B. Describe how the data collected. Okay, so this is what I'm going to do. So I'm going to say plot V as a function of I. So we're going to say by V equals IR and R equals rho 1 LA. That's on your equation sheet. V is equal to rho 1 L divided by A, which is times R, times I, and therefore slope equals rho 1, rho 1 times L divided by A, and therefore A times slope divided by length is equal to rho 1. Bang. Done. So that's pretty much it. That's all you need there. But that's what I was getting at, you know. So that's why you need V and I. And you have to say, sorry, earlier I didn't say this. You have to connect the voltmeter like this. They want to hear you say the voltmeter should be connected in parallel with the battery. Cannot be in series. That is not how the voltmeter works. But the ammeter is connected in series. Make sure you say that. Okay. In experiment 2, the students are asked to use a graph to determine the resistivity of rho 2 of a solid cylindrical resistors made of the same material but different lengths L. The cross-sectional area of each resistor is this number, and the students directly measure the resistance R between the ends of the resistor. Table 1 provides L and R for each resistor. Indicate two quantities. Okay, so they're asking indicate two quantities either measure quantities from table 1 or additional calculated quantities that could be graphed to produce a single line that could be used to determine rho 2. So here's what we want to say, C. So let's think about this. Actually, this is my strategy. We're going to go skip to part D because I know what they're going to ask next. So College Board has this thing. This is a method I kind of devised myself. On question 3, they will always ask a linearization question. They're going to start with, okay, we're going to give you the situation. We want you to first figure out how to graph or get this value from like linearizing given this situation. The second situation that they gave us here might be the same as the first. In this situation, it looks like the same, but they're just measuring resistance, not voltage and current. So the second situation might look the same or similar, but that doesn't matter. You just know that this question is independent of this question, A and B is independent of that one. So when you get to this question, they're going to give you in experiment 2 or whatever, they're going to tell you we have these values and we want you to find this, right? You're going to skip to part D and you're going to just start linearizing from the equations you know there because you're going to do it before you even indicate your quantities. So why not just save time and write it where you need to write it because you get a point for linearizing in part D. So I'm going to skip to part D and I'm going to go rho 1 LA. So if you plot R as a function of L, because I don't want to do more extra linearizing, then I can say this is y equals mx, and this is what you should be writing. You should be writing slope is equal to r1 a, and a times slope equals r1. And now you'll write something else, like slope is equal to the change in resistance over the change in length. So because this is y, this is m, this is x. So now that I've identified that, I know vertical axis goes r, horizontal axis goes m, or L, whatever it is. And there we go. This is how you want to write them. You want to include the units. And now when I write delta R over delta L, I'll pull from my graph. I'll pull points from my graph in order to find the slope. So now we're going to actually have to graph, which is the part I don't like. So it's going to say on the grid provided. And if I went through this too quickly, please just let me know. But I hope it made sense. So on the grid provided, create a graph of the quantities indicated in part CI. Use table 2 to measure. Okay, so this is what we're going to do. We know that resistance has to be on the Y, so I want to include that there. So they gave you points. So for putting resistance on the Y axis, and for putting this on the X axis, and including the units of measurement. So there we go. So there's that. And now clearly label the axis, including units as appropriate. Plot the okay. So now I'm just going to plot these values. So how am I going to scale my graph? That's the real question. I'm going to go by fives. I'm going to go 1, 2, 3, 4, 5. There, cut that off there. 1, 2, 3, 4, 5. Cut that off there. This is the strategy you could use on the AP exam. It makes graphing way easier. This is what I did. It's a really bad graph. They should cut it into 5 for you already. I don't know why they don't, but you know, let the kids waste time because we gave them 100 minutes. I don't know. College Board hates us, but it's whatever. So now, logically, I'm just going to go 1, 2, 3, 4, 5, 6. And you might be thinking, well, hey, but you're not using most of the graph. It doesn't matter. They don't They don't care as long as you use half of it. And I'm banking on the fact that I'm about to use half of it. I don't know if I'm about to use half of it. I hope I am about to use half of it. That's what I said on the exam, and that's what we're going to do here. So now, if you can see here, this goes from 0 0.1, 0 0.2, 0 0.3. This is free, is what I'm saying. So we're just going to go 0 0.1, 0 0.2, 0 0.3, 0 0.4, 0 0.5, 0 0.6. Great. Now we're going to look at our values, and we're going to think, well, what's our values? So we have 0 0.1 comes 0 0.9, so that's like there. We have 0. Oh, oops, I didn't do, okay, so it's 0 0.01, 0 0.02, 0 0.03. Make sure you don't make that mistake. That is a horrible mistake that might actually cost you like a couple points, so do that. But yeah, because these had the 0 before it, okay. So now 0 0.02 will correspond to 1.6, so that's like 0 0.02. I know that 1 divided by 5 is like 0 0.2 because this will each increment by 0 0.2. So this is 1.2, 1.4, 1.6. Now 0 0.3 corresponds to 2.5. 2.5 is like in the middle of 2 and 3, so 0 0.3 corresponds to, oh, this is hard to visualize, like here. 0 0.04 corresponds to 3.2? Okay, 3.2. 0 0.04 corresponds to, and I know that they increment by 3.2. That's the way I designed my graph. And I know 0 0.05 corresponds to 4. That's a bit of an easier one. That's like 0 0.05. Oh, I lost it. It's up there. 0.5 is like here. Okay, so now if you notice we did this right, this is a linear graph. And we're just gonna draw our line of best fit like this. Bang. Pretty easy. So now that we've done that, we're gonna use the slope now. We're gonna pull points from the graph. Okay, here's one. So, oh, that's so much work. Okay. So here's 0. This is 0. I'm calling that 0, 0. Here's 0 0.2, 0 0.4. So that's 0 0.4 on the y. And here, it's like 0 0.04. 0 0.004. And if you're asking how I got that, I'm thinking, okay, well, 0 0.01, I have 5 cubes here, so 0 0.01 divided by 5 will give me 0 0.002, and if I have 2 cubes, I just went by 2 cubes, that's 0 0.04. So now I'll pull my slope here. I'll put, this is 0.1, so I'll record 0.1. They want to see you record the points. Now I'll go and record 0.2. Oh my gosh, see, I hate this. I hate this like recording points thing. It's so annoying. So that's 0 0.06 on my x. So this is 4 point. So this is it's like in between. It's in between. Like here was 4.6 and 4.8. Call it 4.7. So now I'm gonna record. I'm gonna do rise 4.7 minus the other y, which is 0 0.4, over run 0 0.06 minus 0 0.004. And that will give me a slope of, we're about to find out. I'm going to use Desmos. Normally, you guys would know I have it like usually on the side, but this exam was digital, so obviously we didn't get it. That's fine. Which gives me 6.78, which is not a good number, but that doesn't matter. So this is our slope. And now, like I said earlier, if I multiply a by that slope, which was, what's the number? 5 times 10 to the negative 6 times 7, 6.785 is roughly equal to, and I'll multiply that on decimals. 3.839 times 10 to the negative fourth. And resistivity is in ohm meters. And there we go. That's pretty much all you need for that question. All right, guys, excuse the technical difficulties. Yeah, I was worried because I thought I got that question wrong, but no, I think I did it right. I was just looking at the key and I made a mistake on the key, which is fine. So now we're going to read this question. Question 4, almost finished. Long parallel wires S and T are a distance 2D apart. Both wires carry equal currents I, but the currents are in opposite directions. Both wires are parallel to the x-axis at the instant shown, as shown in figure 1. Sphere 1 is a distance d above wire S, and sphere 2 is a distance d below wire S, and both spheres are moving with speed v in the negative x direction. Okay, in the positive x direction. Each sphere has a positive charge plus q, and gravitational effects are negligible. F1 is the magnitude of the magnetic force exerted on sphere 1 due to the currents in wires S and T. The F2 is the magnitude of the magnetic force exerted on sphere 2 due to the currents in S and T. Indicate whether F2 is greater than, less than, or equal to F1 by writing one of the following. Justify your answer. Okay, so when they say justify your answer, they're giving you free range to just use equations however you want. So let's think intuitively here. Using our right-hand rule, the magnetic field that wire T creates at sphere 2 is pointed down. And the magnetic field that wire S creates is also pointed down. But the magnetic field that wire T creates at sphere 1 is pointed down. But the magnetic field that S creates at sphere 1 is pointed up. So now we're going to say, oh my gosh, wrong thingy. We're going to say F2 is greater than F1 as B2 is greater than B1 by RHR. The B that B as in magnetic field S and T creates at sphere 2 are in the same direction. But at sphere 1, they are in opposite direction. Opposite directions with less overall magnitude. Therefore, by FB equals the charge VB sine theta, and that's just an equation on your equation sheet. Since Q1 equals Q2, F2 is greater than F1. And hopefully that makes sense that you could say this in your answer. I'm just not going to say it because I think that's enough reasoning for them. The magnetic field is at a distance d here. They're both at distance d. But so the magnetic field that wire S creates here is the same magnetic field that wire S creates here. But the magnetic field that wire T creates will be less because now it's 3D away, right? And we know that B wire is mu naught I over 2 pi r, right? So it's proportional to 1 over r. So more distance equals less magnetic field. So the entire point is that since this wire is now further away and they're in opposite directions, right? The magnetic field overall will be less, therefore the force will be less for F1, therefore F2 is greater than F1. So that's that question done. Now, if they were to say justify your answer without beyond referencing like physics equations and using qualitative reasoning, then that would be a different story. You can't use these equations. You have to like reason it out. But I think they said justify your answer because like what other way would you reason it out unless you're like Max Planck? You know what I mean? But yeah, B. So derive an expression for the magnetic field at the location of sphere 2 due to the current in wires ST in terms of dI and physical constants as appropriate. Begin your derivation by writing a fundamental physics principle or an equation from the reference information. Okay, so here's the fundamental physics principle. Mu naught I over 2 pi r equals B wire. This isn't on the equation sheet, but you should know this. This is derived from Ampere's law. So let's just use that. So B total. So now B total at point 2 is equal to BT plus BS. And we know T, wire T, since they're in the same direction, we can just add them, right? It doesn't matter. Because right-hand rule, this one will point into the page. Right-hand rule, the other one will also point into the page. Right, I'm going to call that like that. Okay. So now I'm just going to do a little bit of algebra. So mu naught I, since they have the same current, right? It said they have the same current. Yeah, equal currents. Divided by, okay, and it's 2 pi r, 2 pi d plus mu naught I over 2 pi d is equal to 2 mu naught I over 2 pi d. Oh, well, the 2 cancels, and that's equal to mu naught I over pi d. Great, there's your final answer. Done. Nothing more besides that. Part C. Later, a wire T carries a current 3I in the positive x direction. At the instance shown in figure 2, sphere 2 is a distance d below the wire S and moving with the speed v in the, in the positive x direction. F nu is the new magnitude of the magnetic force exerted on sphere 2 due to the currents in wire T and S. Okay. So basically, okay, so wire T carries current in the positive x direction now. So now they're both moving in the same direction. So let's use our right-hand rule just to logic the situation out before we even look at it. So that one will point into the page, and from there, that one, wire T, will come out of the page. Oops, wrong color. Wire T will come out of the page. So now we have to subtract their magnitudes, right? So C, indicate whether F nu. So before I even indicate, I'm going to leave a space here to indicate, and I'm going to just start deriving the thingy, and then I'll reference the thing. So B at 2 is now equal to BS. Or no, we're going to say BT minus BS, which is equal to mu naught I, or no, mu naught 3 mu naught I, because wire T now carries 3I and the current of the other one was changed, divided by, well, the distance is still 2 pi d, so we're going to take that and subtract it from mu naught I over 2 pi d, because that one didn't change besides its direction. So now this is going to give us 2 mu naught I over 2 pi d in the positive. So now the magnetic field is coming out instead of going in. So which is equal to mu naught I over pi d. So now, then we're going to box that. Since B2 slash B new is equal to B old slash B totes, mu naught I over pi d is equal to, I'm just putting this in parentheses because they said to reference it. I just want to make sure you guys reference it. So because these two expressions are equal, therefore FB is equal to F2 is equal to F new, as FB equals QVB sine theta, and neither Q, V, or B changed, or sine theta. Bang! And that is everything on this AP Physics C 2025 E&M. Yeah, E&M. Exam. It was honestly like when I took it, it wasn't that bad. Um, because it was like I think it was fun. I like taking these exams. That's why I make these videos. But hopefully you guys are ready for this upcoming 25-26 year. And I hope this helped even a little bit. So yeah, that was it. Let me know if you guys have any questions, and I'll catch y'all in the next video. Bye bye.